One of the biggest things I learned when I was a founder was the things that people walking up and down the halls at MIT think about all day and just kind of assume are happening and are going to happen. That gap between that and industry and the outside world is much greater than I thought.
Most robotics demos never ship. Deployed is about the ones that do. This is Deployed, where physical AI gets real. I'm incredibly excited for this conversation with Dr. David Mindell, professor at MIT, founder, CEO, investor, engineer, historian. In your book, you also mentioned that you fly airplanes, play electric guitar. I don't know how you have time to do all this. But I first met Professor Mindell as a student in a class called The Structure of Engineering Revolutions, loosely structured off of Thomas Kuhn's work on the structure of scientific revolutions. And we've read a number of other books, Soul of a New Machine, and then ended with a final project. I want to talk about that final project at some point, because what we learned in that was that there is no separating technology and technology change from the human stories, from the social stories. And obviously your writing touches on that. You last year published the new Lunar Society. Give us a little bit kind of your inspiration for this book and how you kind of tie history to the modern day and what compelled you to tell that story.
Sometimes people ask me if that was my pandemic book, and it really wasn't. It came out after, even the idea for it came after the pandemic. We had just started this investment firm, Unless, and we're trying to find a way to get an identity for that. And I was like, well, let's just have a series of dinners and invite people who are interesting from the community here and elsewhere. And, one thing leading to another, let's call those dinners the Lunar Society. I had read a really pretty great book by an English writer named Jenny Uglow about 20 years ago about this group. And let's just call it the Lunar Society, named after this original group. And then, as I often do when I get into these historical topics, I just couldn't stop. And I kept diving deeper and deeper. Jenny Uglow's book, The Lunar Men, is a great book, but it focuses more on the biology and the natural sciences. And as a historian of technology and industrial historian, I was like, there's amazing connections here, not only to industry, but also to the foundation of American democracy. There had been other work in the 60s, actually, which was really good about these guys were basically like the first industrial research organization. There's an amazing group here, and there's a great tradition at MIT thinking about industrial change, thinking about work, thinking about industrial policy, which has been growing all during these years. And I felt there was a place to kind of report some of that out to a community of readers who don't usually read about that stuff. So, you were at this conference yesterday. There's, hundreds of people around. All they think about is supply chain, automation, AI. But most people don't. Coming out of the pandemic, suddenly everybody's talking about supply chains. Mm-hmm, mm-hmm. And I had an old 90-year-old aunt at a family event said, tell me, what is this about the chain supply? And, supply chain was a sort of exotic professional term for a few academics and a few industry professionals. And suddenly it's on everybody's lips because they're breaking down.
Right.
And you can't get toilet paper. Suddenly these kind of sinews of the industrial world become visible when they break down.
Right.
At the same time that we have AI and the invasion of Ukraine, and things got to change. And they got to change pretty quickly. And the world is kind of jolted out of its slumber on some of this. So I took it on myself as a writing challenge to say, let's tell this 18th century story where James Watt, Matthew Boulton, Benjamin Franklin, Joseph Priestley, Josiah Wedgwood, Maria Edgeworth, incredible group of people. It wasn't industry 2.0 to 3.0 or 3.0 to 4.0. They went from no industry to industrial. And what did that look like? And, they were dealing with pandemics. The French Revolution happened. The American Revolution happened. It was not a happy time for the world. I think the thing that really struck me about them is they were builders. They got together to build, and they just wanted to build.
Yep.
And that's sort of what I see here at MIT. The students, they'll take our classes, get their degrees, only in as far as it helps them do what they want, which is build.
Right.
And we have to help them figure out how to monetize it and turn it into business and make it useful and productive. But building is it's not the only drive, but it's a pretty big one.
That it really is like a classic deep tech story, right? James Watt had this idea, how to attach a condenser and maybe make a more efficient steam engine. But at the time, like, we really didn't quite understand how phase changes worked from gas to liquid. It's interesting, as we were setting this up, we were a little worried because the heaters had just come on, right? These steam heaters in this room, and like gurgling and bubbling, and like, people don't think about steam as a tool, but that transition from liquid to gas can release a lot of energy, right? And yet at the same time, we didn't know how to do it, and James Watt didn't know how to do it. And he brings an investor, John Roebuck, and then at some point in the book you mentioned that, the investor piqued his interest when he heard there might be another investor interested, right?
Sound familiar?
Maybe I can bring someone else in to help. And so how did, I guess, Boulton had tried to build some of his own, and so, but James Watt didn't seem like the easiest person to engage with. Why did people maybe believe he could do it? Like, what was it about him that did get them compelled?
I sort of start the book with the heroic inventor story. James Watt is the first inventor memorialized in Westminster Abbey. I mean, he's a big deal in English culture and generally in technical culture.
I mean, we named the Watt after.
Everything we talk about when we talk about energy is in his name. And I think that you miss a lot when you just sort of portray him as this lone hero with this individual. He described his own eureka moment. And when you really look at it, and you don't have to read that much into the documents, there's no doubt he was a brilliant inventor, designer, engineer. He deserves all those accolades. There's no debunking. But he's a very complicated person, and he couldn't do it on his own. And he knew that. And he didn't manage workers well. He was kind of arrogant. He didn't really understand what he called engineering and great, which is he was an instrument maker, and he made a working model of his condenser. But then he had to build one the size of a building. That's a whole different story. And he gets matched up with an investor, as you mentioned, John Roebuck, who's not technical and is interested in the financial aspect, but doesn't really get it, and doesn't really support him financially or otherwise. Then through the Lunar Society, he meets Matthew Boulton. And Boulton is a manufacturer, and he needs this because he's running off canals and water power, and it's very poor capital utilization in the winter and the summer. He's been experimenting with steam. He had a prepared mind, and the personality match, for whatever reason, worked. Boulton is like bubbly and outgoing and optimistic even when his business is crashing. And Watt is like diffident and depressed and inward looking. And at one point, and this is an astonishing thing to find that you don't read about with startups today, but I'm sure it happens. Watt's wife writes to Matthew Boulton, his business partner, and says, "I'm worried about my husband. I think he's suicidal." There was just this deep emotional well that they had to go through to get this engine not only working, but then commercialized. Those aspects of it make the story more human. Many of us founders can relate to those emotional roller coasters.
Because they were, 15 plus years, right? Before there was any real commercial viability.
And they get it working in the mining. And Watt, is 20 years in at this point. And Watt's like, "I'm done. Like, I paid off my debts. I got a little money. We're good." And Boulton says, No. This thing is not for mining. This thing is for running factories. And to do that, I need a rotative engine. And there's a great historian who wrote about this who said, Boulton drags Watt kicking and screaming across the threshold of his own mediocrity into greatness. And he drags Watt back to Birmingham and, metaphorically speaking, locks him in a room, which is fine. That's where Watt likes to work. And the next 4 years are the most inventive years of his career. And he makes these 4 inventions that are just absolutely crucial, subsidiary, but fundamental inventions to make the engine practical. And that's 20 years after his original separate condenser idea. And again, we can all relate to that. Like, it's all that stuff that's key. You can have the big idea, but it's those many, many small improvements, innovations that you learn by the deployment that actually is what makes it work.
A couple of things you point to in this book innovation in measuring tools, right? And innovation in precision, being able to build the bells and the condensers with enough precision to seal. I think in the AI world, we don't think as much about precision in tooling and in manufacturing, but it has driven a huge number of these transformations. Can you draw a through line in some of that early work and what we're seeing now?
A steam engine has to be a mechanically precise machine. There was no sense of precision when they started making these engines. The valves had to fit together very precisely. The pistons, which were quite large, like 100 inches across, had to fit into the cylinder. The cylinder had to be both circular and true. They really had to invent the machine tool industry in order to make these things at all.
I mean, at one point you mentioned that, they measured in the width of a coin, right? What the tolerance was.
So there's no idea of mechanical tolerances at the time. There's no mechanical drawings. Watt's constantly complaining that the workmen aren't building what he wants, but he doesn't have a formal way to specify that. He actually does a lot of innovation in mechanical drawing over the course of this period, and you can certainly credit him with a lot of the beginnings of the conventions of what is quite sophisticated technology, a modern mechanical drawing in CAD or on paper. The screw micrometer, those little things that look like a little C, that's a Watt invention from this period that people still use. And then the other piece of that, which is also a common thread, is not only ever increasing precision, but the ability to manage precision with cost, because precision is quite often expensive. It's almost by definition expensive when it's pushing the state of the art. So you don't always want the most precise thing that you can possibly do. You want to be able to find your place on the precision cost curve. That's where you need it to be. And that requires a lot of different concepts and tools that had to be invented, over a 100-year period, really. I started my career doing robotics in the deep ocean. And the first thing I was assigned really in my first job at Woods Hole was build a very high precision navigation system. And we were able to measure millimeters by sending very high frequency ultrasound pulses through the ocean, which was somewhat of a departure from traditional sonars, which are much lower frequency, much longer wavelength, and actually much narrower bandwidth. And so you need high bandwidth to make precise measurements. Archaeologists, oceanographers we'd work with would say, I don't need to know where my robot is to within a centimeter. And we'd say, okay. With Dana Yerger, we gradually developed control systems that could make the robot hover within these very precise and move very slowly while you scanned an ancient Roman shipwreck or a hydrothermal vent with all kinds of crazy sensors. And the slower you could go, the higher data density and the more time you had to integrate. And what we ended up with was, how about a map of your hydrothermal vent that's accurate to a centimeter? Oh, yeah, that starts to get interesting. Well, that's the same thing. We made chemical maps of hydrothermal vent plumes by driving through the plumes in 3D and measuring chemical concentrations. Nobody had ever done that before. I just got locked in my head this idea that when you end up with something that is more precise than most people think they need, there's information in there that you had never thought you needed. I developed that technology commercially for 10 or 15 years, never particularly successfully. But then I said I always want to do this with RF and not sonar, because sonar is a crappy modality. The frequencies are kind of low. The transducers aren't very good. And the water moves around. And that's the limit on your precision, is really the motion, the kind of micro turbulence of your water channel. About 10 years ago, actually more like 15 years ago, started playing around with doing that with RF. Found a great partner, Greg Sharvat, who was coming out of Lincoln Labs, who had just written the first ever book on small and short range radar. And we developed this thing where we could get, it's now into the tens of microns of resolution on range measurement with some pretty inexpensive, simple millimeter wave sensors. When you measure tens of microns, you can see the vibration on your table as the truck goes by outside on the street. You can measure people walking around. You can measure these very subtle forces on a beam that make these very slight deflections. And if you hold on to it in air, you can see your breathing, your pulse, your balance, all signals just in a simple range, much less triangulating that into 3D. Then the kind of business of the company became extracting as much information as you can out of very precise sensors. Long story short, we end up with not even particularly expensive, but pretty good inertial measurement units on subway trains and transit cars in general, streaming a lot of that data to the cloud and integrating it over just normal daily use. And guess what? You measure the condition of the track with incredible precision at very low cost. And you can find, bends, cracks, bumps, things as they're developing very slowly, just because that sensitive, really just acceleration measurement repeated enough times in the same spot gives you really valuable data for, essentially predictive maintenance. That's all from this idea that precision in measurement always teaches you more than you think you need.
In conveyor belt systems, pretty common to just attach vibration meters, flow the data in, and to identify problems much earlier as a result. But fascinating to do that on a moving train with high precision RF. In a software world, it's easy to just kind of abstract all that hardware complexity and all that operational complexity. But when it comes to actually deploying robots in the real world, those small drifts in odometer readings, LiDARs give great kind of distance and depth, but the dimensions of the base kind of vary a bit.
The sheer just like dirty physics of that environment was so demanding. Everything from 18-hour days to, how do you calibrate an inclinometer when you've been on a ship at sea for 3 weeks? You can do it because you hope the ship has got a zero mean roll, but every one of those was a problem. You left a hair or a speck of dust on an O-ring at those pressures, you suddenly had a housing full of seawater, and seawater and electronics don't get along that well, it turns out. So much of what we did was just contingent on those details. And one of the great strengths of Woods Hole was that it's an academic institution. I work for Dana Yerger, who's an MIT PhD, but it also has this great component of like old Massachusetts maritime operational culture. And there are all of these great technicians and ship operators who just come from these seafaring families. They've been going to sea their whole lives. And they've then spent their career helping scientists do weird things. So how do you safely drop even just a 1,000-foot line off a ship and get it back just to test something? How do you safely tap into the ship's navigation system? We would control the ship from our little robot controlling. So, an IBM PC at the time, you hit return and the ship would move 3 meters. And it was that collaboration between that really operational culture and the research culture that made that place very special. And like MIT doesn't have that, right? MIT is a laboratory environment. We like to take the students into the field, but it's all sort of one-off, whereas in the expeditionary culture there, people are going to sea all the time, hundreds of days per year. The cadence, of course, gives you an ability to learn that's very hard to do otherwise. The simplest things were just so hard. And, there were these incredible moments where, we're off the Straits of Juan de Fuca on the Juan de Fuca Ridge in August, where the seas are only 25 feet high and going down about 2,500 meters. And you get the robot to hover for the first time at the end of a 2-mile cable. And all these little pieces are working at the same moment. And you're like, whoa, like, don't touch it. Finally, everything locks in it. And I knew it at the time. That was just an amazing education for a young engineer to be hit with that. And then you come to MIT or work with a startup. And certainly in the worlds that we are in factories, warehouses, hospitals, like it all takes that. And then it's even more complicated because at least in the deep ocean, there are no people. And then you go into these environments where there's people walking around trying to do their jobs, and so much depends on that deployment process. That's really where so much of the innovation has to take place.
Yeah.
Even if they're little innovations like, put a green light on it so when it turns on, you know if it's working,
Right. Right.
The people who embrace that and do that well, I think, are the people who ultimately win, because a place like MIT is full of great ideas and full of people who can make those things work in isolation, which is a key first moment. But in the physical settings and that we're talking about these days, so much depends on all of these details being managed and nuanced. And you feel it when you work with a machine or even a car that's really well designed, that just like gets all that, and they hit a sweet spot for it. James Watt was dealing with that stuff right and left.
I just spoke with Scarlett Kohler recently, who's a
Former student of mine.
founder and CEO of Mithril. She was an intern for me on Prime Air.
Oh, cool. I didn't know that.
And as a sophomore, she got a patent on, because they tried to do tether drop from a drone. And they realized that the harmonics and the controls meant if you weren't controlling both ends of it, you were subject to all kinds of problems, right?
Yeah.
And so you're describing the same phenomenon on a tethered, submersible, right? These are complex controls problems that you can try to model all the physics, but you've also got to just tune some of these controls. Having experienced machinists, right? Having, like, there was a talk of James Watt eventually getting access to kind of better labor. Silicon Valley has such a bias toward first principles thinking, but combining first principles thinking with the experience of what actually works, right? It's like, yes, realistically a LiDAR should be able to give you that, but yeah, there's vibration and there are other problems. And odrometry seems like the wheel encoder should be very, very precise, but there's drift in it, and having those folks who have built these systems and have just kind of learned the hard way to tune it differently, or just to simplify, right, it is amazing. So in this course, Structure of Engineering Revolutions, the final project is a deep dive amongst kind of 4 of your classmates into primary source literature. So you go back as a historian. My group studied Thinking Machines Corporation. For the audience that doesn't know, Thinking Machine Corporation was a early supercomputer company, really with a incredibly talent-dense team, right? Cheryl Handler, Danny Hillis, but then, Marvin Minsky was advising them, Richard Feynman, Brewster Kahle was there, Charles Leigerson, who was co-professor in this course. So they built 3 machines, the CM1, Connection Machine 1, the Connection Machine 2, and the Connection Machine 5. And there was a debate that raged. The CM1 used a bit serial architecture, and the CM5 went to a more modern multiprocessor parallel architecture. And we were looking at the CM2, there was a debate raging as to whether to go from bit serial to multiprocessor. And so we're like, okay, this seems interesting problem, but then we go through the primary source material, and there's not a lot on the technical detail of why that debate was going on. And so, we were engineers, we computer scientists mostly, and we had a circuit diagram, but we decided we just needed to call people. We found an article that said in the early 80s, there was an AI conference with 40,000 attendees. We went through an AI winter where nobody was going to AI conferences. Now AI conferences, robotics conferences, 40,000 might be a little small, right? But there were 40,000 people. So we asked Marvin Minsky about this, right? What was the AI community like? And he just goes on a rant that there was never an AI community. I don't think we can put that in our final report, right? I don't think that.
What was his rant about?
He just ranted that there never was an AI community, right? It was just kind of a classic Minsky rant, right? Yeah. Let me just destroy the whole proposition of your question and then not answer it, right?
Exactly.
We talked to some of the leaders and executives, and then all they wanted to talk about, they didn't want to talk about the architecture. They wanted to talk about why the company failed, because this was about 5 years after. So it was like this perfect window where people were still, they had gotten enough perspective, but they wanted to tell somebody. So they started telling us all these stories, right? Some of the stories are one just blames the whole thing on Al Gore, right? Al Gore had committed to if they got elected by a bunch of these machines, and then, it doesn't come through. And so they're just angry with Al Gore. And I don't think we can write our final report on that. That's not, somebody posited there was a love triangle going on. We're okay, we're not going to put that in the final paper either. And at some point there's a whole discussion as to whether Dr. Leigerson was actually helpful or was actually steering them in the wrong direction. And we're I don't think we're going to talk about our professor in this in this paper either. And then we finally get to one of the architects who's deep in this debate, and we're just asking about the architect. And he just starts breaking down in tears on the phone. as if kind of this decision in the CM2 somehow undermined the fortunes of the company, which I think, given all the other dynamics, was he'd taken way too much of the blame on himself. The lesson in all this is that there is no technology story that's not a human story. We think about like OpenAI and the kind of the drama around this, the board moving Sam Altman out and then bringing him back in. We're never going to know the full story behind all of that. And this was where you went and kind of New Lunar Society, is that it's not just process innovation, it's not just technology innovation, but the social dynamics, both the local dynamics and the macro dynamics. You had some, interesting dynamics between engineers and between leaders that were complicated human dynamics, but then you had these macro dynamics of the Cold War kind of ending, and particularly as we go into this age of AI, like, is it worth trying to separate the human story from the technology story, or are they just always infused and we kind of have to study both?
Well, I mean, obviously we separate out the technology to teach engineering at some level, and there are principles that you want to teach in a classroom that are, best learned. Although even those principles, we teach electrical engineering and we have volts and watts and coulombs and amperes, and those are all people, right? So it's hard, even down in the nitty gritty, knowing who those people are actually enhances the learning, I think. But there's pedagogical reasons to focus on the concepts. But when, again, you talk about deploying technology into the world, all these things come into play. And I mean, the reason I'm a historian is that I just think historical narratives capture the complexity of these technologies in the best way that I know. There are other ways to do it as well, but for me, it's this story of lab to market, however you want to describe it, that is the essence of what it takes to make stuff work. And every time you look at something that worked, it has as much to do with those execution phases and the relationships. And the relationships are human and turbulent, but also really rich, and people support each other and feed off each other in both positive and negative ways. And those relationships are also embodied in the technologies themselves. So many examples, but the shape of the wings on the space shuttle are a product of NASA's negotiations with the Air Force in the course of getting it funded. It turns out they're way too big to accomplish what the space shuttle really needed, and they're carrying these giant wings into orbit every single flight because of stuff that happened 20 years before. I think that's maybe even doubly true with AI. These are human-created systems. They are created for particular purposes, and they carry within them values, goals, hopes, dreams, aspirations of the people who made them. Sometimes they're successful and sometimes they're not. And sometimes they're successful for a little while and then they're not. It's very valuable, I think, to teach students to see that, right? I remember you in that class, and you were an excellent student in that class. And it's been a thrill to follow your career since then. I'm by no means the only one who teaches that kind of thing around here. There's a lot of different ways to do it, but I think it makes people better engineers. Because you always end up managing something if you're doing anything but sitting in a room by yourself. All technologies are really created collaboratively, and even a little bit of sensitivity to the importance of these dynamics. And they're a huge pain in the butt, and they consume a lot of our energy. But boy, when they work well, it's an amazing thing, even if it's only for a few moments.
A few years ago, you started investing as well. And so I'm curious if that kind of changed your perspective on any of this. What do you think about when talking to founders and deciding, whether something's worth investing behind?
Yeah, great question. For all the things we've been talking about that I've done, a lot of them were my childhood dreams. Starting a company was a childhood dream. Even studying history and writing my books and building electronics, those are all childhood dreams. Being an investor was never one of my childhood dreams. It kind of came to me after I stepped aside as CEO at Humatics. My largest investor in that company, Trevor Zimmerman, I joined their fund as an operating partner, but then he and I ended up splitting off and founding this fund, Unless, together. We focus specifically on industrial technology, transformation of industrial systems, lots of different kinds of industrial systems. And so at some level, we're focused on this same process of, we don't think of it as having a lot of technology risk. Sometimes we're better able to assess that other people think that looks crazy. And we're like, actually, no, that's pretty much done, but there's a lot of work to do in actually scaling it into transforming an industrial system. And that's often what we underwrite. Sometimes they say my investor job is very similar to my professor job in that you're sort of advising, mentoring, helping young people in their 20s and 30s who are very, very smart and well prepared, but going through this, grueling process of bringing stuff to market. I love just generally hearing the pitches and knowing what's going on. And there's an interesting kind of discipline in having that prepared mind. You think about Matthew Boulton a lot. So you know what the landscape is, you know what's interesting, you know what some unsolved problems are, but letting the founders tell you what the solutions are, what the new things are. I say this in the book about Boulton, but I think about it a lot. Matthew Boulton had the humility to know when excellence had come to him. And when he met James Watt, even though Watt was like not a great communicator and depressed and lonely, and Watt was like, this guy has it. He's got it, right? That's a really hard, special thing to be able to do, to sort of be on the lookout for people like that, for technologies like that, for groups of people like that is a really interesting challenge, and also forces your brain into lots of different technology areas. I feel like I can only stray so far from the things that I know about, robotics, electronics, sensing, manufacturing, warehousing, so on. And then we have to find other people who can help us, more in the life sciences and bio and sort of things. But these are interesting areas now anyway. One thing I've always really liked doing is making connections between things across technologies. Not just technologies, but people and technologies, and trying to understand, maybe somebody thinks they've solved a small problem, but actually they could use that small problem to solve a big problem.
There's a line in the book that stood out to me because it felt still true, that these industrial transformations often take 30 years. I was chatting with Jeff Wilke recently, really the architect behind Amazon's logistics engine, and then Amazon just announced that it's opening up that logistics engine to anyone who wants to use that. And Jeff and I, after leaving Amazon, have both been walking other warehouses, other people's operations. And Jeff made a comment to me. He said, because I said, Jeff, I can't believe what I'm seeing. For instance, we walked $12 billion a year company in the logistics space, the 500,000 square foot building, not connected to the internet. They're faxing work orders between. And Jeff said, he's like, at Amazon, I really thought we were maybe 5 years ahead. Yeah. He was like, not much change. Talking to another founder who, was pointing out that robotic arms, the eligible work that those could do versus the actual penetration, he estimates is about 10%, right? In other words, 90% of the opportunity for where robot arms could take on work is not addressed in North America right now with that technology. So what is it that elongates these? Because you're careful not to say in consumer spaces, or you kind of qualified it to these industrial transformations. And so I'm curious if there's something about the dynamics there that you've observed.
First of all, just industrial systems are big, and they have a lot of embedded capital, and it's expensive to change them. And there's also this imperative of if I'm delivering 5 million people a day to work with the New York City subway system, it's hard to change that. New York City subway happens to be 24/7 operation. Very hard to change that without imperiling the mission. One thing leads to another, and suddenly you got 100-year-old relay switches operating those systems that every time one of them breaks, you got to go just machine a new one if you can find the drawings. The critical systems have to be changed incrementally in some way. They're very brown, the brownest of the brownfield. I use this rule of thumb of 30 years from when a technology is working, not the hard development part, but that's what it takes to proliferate through. I mean, Amazon's 30 years old now, more actually. But it also happens to be about a human career cycle. Mm-hmm. So there is just this element of, back to Thomas Kuhn, somebody asked him, so when you talk about these revolutions between incompatible paradigms, what makes people change? When do people convert from paradigms? and I think this is even in the book. He says, well, they don't really change; they just die. And I think
Right.
that's actually a very important component of all these things we're talking about is generational change.
Right.
The kids are coming up; they want to do things in new ways. The old people are like, that doesn't work. You don't know what you're talking about, and both are right. And yet, over time, and just about the same time it takes for the old folks to retire is what it takes for the young folks to both learn the parts that are hard and refine the techniques. And over time, you see that change. Again, that's partly what being a historian is about, is ultimately trying to understand technological change. I just use this phrase these days, human time. I need to go find a new customer. Well, that's 3 meetings. Each meeting takes a week to set up the call. Then it takes 6-12 months for the pilot, and you build the relationship. And the relationship is as much about calendar time working together as it is about milestones. And you add all that stuff up, and these things, they're not, at least in the areas that we work in, they're not as accelerated as you might think from earlier eras.
Right.
I can write code so much faster. I can do so many things so much faster. But bringing new technology into, critical human economic environments, there are still these dynamics. Now, is it worth thinking about how to change that and accelerate it using tech? Of course. And we certainly do in certain places. But there's also just this human time element of the seasons change, the young people become the old people. And again, as an investor, you kind of look for that. What are the things that actually have been around for a while? Parallel computing, one example. But, it didn't succeed here, there, and there. But, maybe it really is time for it now. And that happens all the time.
You helped co-lead some work at MIT on workforce transformation. Mm-hmm. What were maybe some of the surprising elements or the insights that you it's easy to go into those with preconceived notions and then try to find evidence that supports those notions. But I'm sure as engineers and scientists, you pursued it more from fundamentals. What maybe surprised you in the work?
Well, we went into that in 2018. People were literally coming up to Raphael Reif, the president of MIT, saying, I need MIT to tell me if a robot is going to take my job. And one thing led to another, and he appointed us to put together this task force. Me, Liz Reynolds, who's a policy expert, and David Autor, who's a great labor economist. And we assembled a group of researchers here. We assembled an outside industry advisory board, which there was so much interest. We had the CEO of IBM, CEO of Pepsi. People really cared. This is 2018. The robots are coming, right? And yet another one of the waves of the robots are coming. David Autor had been working on this for a long time, and he's like, look, the problem is going to be not enough robots. Like, the demographics are not in our favor here. We are going to be suffering from a labor shortage, labor scarcity for as long as we can see. It's hard to do research on the future, but one of the few things about the future is how many 20-year-olds are there going to be in 20 years. Mm-hmm, mm-hmm. And there aren't going to be enough. And then you have the pandemic, and then you have increasing restrictions on immigration. The workforce lost 1 million workers during the pandemic. Mm-hmm, That's not a small number, either to just death from COVID or to early retirements. So we're going to have to automate. And actually, this task force went on for 4 years, and that pandemic happened in the middle of those 4 years. And it was amazing because early in the pandemic, June of 2020, there's this huge spike in unemployment.
Right.
There's 20 million people unemployed. And then it goes away, and right back to the employment levels we've been at. It's like an impulse response test of the labor market that you never have any other way from a control systems class. So obviously that favors robotics and automation. And we still have workforce challenges. Like, the biggest problem in half these conversations is, how do we educate the workforce? How do we train people into the new jobs that we're going to be creating? We went through that. MIT has one of the largest and best cognitive science departments in the world. I think it's 100 faculty or more. There's one person who spends a quarter of his time studying adult learning in that department. We know very little about retraining adults. And it's not an easy thing to do. So there are all these pieces of that. And, again, back to your point about the social and the technological, these two things are like two sides of the same coin. I talk to a lot of manufacturing companies. Every single one of them says, we would grow more if we had more workforce. Of course, then you go, why don't you pay them more? I'm like, no, we can't do that. And so there's a lot of things at work there.
Right. Obviously, AI is pretty incredible technology, and yet very early phases. A lot of concern about workforce disruption, but then real challenges in adoption. What are the questions MIT is getting now, right? And what are the questions you're thinking a lot about in this AI transformation?
Now we're getting a question, is an AI going to take my job, right? And we've heard a lot of those conversations, and those are valuable conversations. One of the conclusions from the Work of the Future project was, yes, it is going to take a lot of jobs, but that's been true. I mean, that's almost the definition of technology, is making a machine do something that a person used to do. It's certainly the economist's definition of productivity is more output for less hours worked. That's a good thing for the economy. And it's painful for the people who are displaced, individually painful. It happened to my dad when he was in his 50s. It was amazing how many people around here have had that experience in their families. It's not an isolated experience. And we need to be better about dealing with those consequences. At the same time, what's made that survivable socially, economically, has been the creation of new industries, new jobs, all through this process. So David Autor points out, if you look at the Bureau of Labor Statistics and their job classifications today, and you look at them in 1945, like 60% of today's jobs didn't exist in 1945. Web developer, cybersecurity analyst, dog walker, yoga therapist. And so there's this very strong imperative that we came out of that project with, like, we have to be creating new jobs and new industries and new forms of work. None of those three things are exactly the same, but they're similar. And I do think that happens. And, we've been through some of this a little bit with prompt engineer. How long did that job last? But what are those new industries, new jobs that will be created? And there are policy questions around what can we do collectively to make sure that that's encouraged and supported. And again, a lot of that change is generational. It's the young people coming out of school. You got to make sure you're supporting and enabling them to do productive work during their productive years.
This has been a fascinating conversation. Congratulations on the new book. For folks who haven't checked out New Lunar Society, it's pick it up. It's an amazing story that ties very deeply to today's challenges. And so thank you so much.
Thank you, Brad. It's been a great pleasure to watch your career. You're one of those people whose career has always surprises me what you're doing next, and that's awesome. But it's all very consistent and continuous. So congratulations on all that.
Thank you.